Albert-Callender, and real reflections why the Schrödinger equation is time reversal invariant.
Okay, thank you. All right, wake up. That reminds me of one. Yeah. So first thing I want to say is thank you very much for the invitation. It's wonderful to come and meet many people I haven't met before, to see Argentina, and especially it's been nice because I haven't been doing that much philosophy of physics in the last year or so, and so I've been teaching it and then preparing for this, and so it reminded me how much I love the subject, and so this has been wonderful, a real gift. Second, I did not fall asleep until 5 a.m. last night because of jet lag, so I will only be able to answer approximately 30% of the questions, and those will be the easy ones, like about my name and stuff. And so, yeah, either way, it could work out. And so the hard questions I will answer in a temporally delayed way by answering tomorrow morning. And then third, yeah, so what I'm going to talk about is why the Schrödinger equation is time reversal invariant in the Valia's pancake sense. And so I'm going to be arguing against my earlier self, that paper that was mentioned before by Christian. So now I think that that paper is kind of wrong. Now you're saying to yourself, well, Craig, you know, why in God's name are you giving a paper talking about you being wrong when you're 22 years ago? You've already been wrong like in a serious way like 10 times already before lunchtime today. You don't have to look so far in the past. And so the thing is, you might find it interesting anyway. Even if you don't care about the pancake, non-pancake thing, you still might have been confused or not been completely comfortable with the whole letting complex conjugation be the time reversal operator in quantum mechanics. And so I'm going to try to give a kind of story about how to make you feel a little bit more comfortable with that. I have to admit, there's still a couple things that are puzzling to me about that, but we'll see. But there's definitely something I think that's interesting. And so I've got three arguments. The first one will occupy the majority of the time. That's the one that's interesting. Then the next one is less interesting, but novel. The third one is the sort of thing you'd think up on the plane because you want three. And in fact, it is the thing I thought of on the plane. Okay, so I don't need to go through this very much, but because we could see this sort of. This is a nice picture from Brian, some of Brian's work where he illustrates the kind of pancake time reversal invariance, where I just take the instantaneous states and I just reshuffle. Think of them as like pancakes and just reshuffle the stack. That's what the operation is. You could then imagine in other contexts, maybe other operations. So for instance, maybe in general relativity, it makes sense to change the temporal orientation along a world line. But anyway, it's some kind of operation. And then you could imagine, then you can think of other things, kind of textbook where you have a time reversal operator operating on the state. And then, what is that and why is it justified is then one of the big issues. So, well, I don't know. We've talked about this so much, I don't even know if I need to go through this. But, so in David's book, he says, what can it possibly mean for a single instantaneous physical situation to be happening backward? And he answers, it's gibberish. And so the idea is, I don't really care what the heck you call a particular symmetry. The symmetry is defined by the operations. Give me the operation and then see what things transform. Call it what you want. But the things should transform only through sort of logic and definition alone, where definition through whatever is nomological in the theory. And so then there's been this disagreement. Maybe a way to sort of put yourself in the mood for thinking about the kind of puzzle is to think about the heat equation. This is the poster child of irreversibility. So when you think irreversibility, this first order in time parabolic equation, it is the most irreversible sort of equation. And so now we look at that equation, and then you look at the Schrödinger equation, and you've got the same kind of form. Now suppose somebody told you that, the heat equation is time reversal invariant, and you said, why? Well, because under time reversal I go from k to minus k. You'd say that's bullshit. But here now you have I. I is dimensionless. I mean, so why would I go to minus I? Seems very strange. And so this puzzled me for a long time. And so I ended up saying that theory is strictly speaking not time reversal invariant, but then there was Wigner invariant, Wigner motion reversal invariant. And so, that sort of thing is nice in the sense that, the time reversal operator is kind of weird, and so maybe saying that it's not actually time reversal is maybe, seemed maybe not such a bad thing to say. Time reversal operator has all these kind of weird consequences, such as that you apply it twice on fermions and it kicks out a minus sign, which is weird if you're thinking in terms of a kind of temporal reflections. But on the other hand, the non-invariance, if there was that non-invariance, is disturbingly hidden. It's always just lurking behind the scenes doing nothing because it gets swamped by Born's rule, the square. And, we call the Schrödinger equation a wave equation. It's not a wave equation, it's a parabolic equation, but it is kind of wave-like. And so there's this sort of thing where it's, the conclusion I had before is not really, one I was always comfortable with. So what I thought I'd do is, the first part of the paper is based on a paper that's coming out in BJPS and called Keeping It Real. And so what I wanted to do is just take complex conjugation out of it, just translate all of quantum mechanics into the real in different ways, or think about things in terms of real numbers, and then we just don't have to think about it. And then can we see what time reversal invariance looks like there, and then translate back into the complex and see what happens. Okay. And so there's this really interesting history that I'm going to sort of put in now here. Interlude. I don't give a hoot about, I don't have a kind of thing where I love real numbers versus complex numbers or anything like that. I love complex numbers, that's fine. In fact, I have a paper which I think people in that literature say is the maximally liberal paper you can have on representation. So how did I start thinking about this? Okay, pandemic sucked. But the only one nice thing was that then we had all these Zoom reading groups and stuff, and so we had Ward Struve from Belgium come and join our group, and he has this nice paper on time symmetry and ontology, and it's mostly about electromagnetism, but he has a little couple paragraphs about quantum mechanics, and I saw this equation, and I thought back to my ancient PhD, and I thought, shoot, that equation would have solved all my problems in one of my chapters. And I then knew that this equation came from another equation because in the 90s, everyone was working on canonical quantum gravity, and not only is there the problem of time, but there's also there's the problem of complexity. There's no I popping out either. And I knew of the Nobel laureate's paper by Yang about this, and so I knew then about this Schrödinger story I'm going to talk about, and then it led on. So let's detour a little bit of history. So it's springtime, late May, June in Zurich, and there's this person. The person was somebody who went for a walk with Ernest McMullen and then repeated it enthusiastically to Elise, and he also discovered quantum mechanics, Schrödinger. And so Schrödinger, in the first half of 1926, basically was just pumping out what became quantum mechanics. So he had these different 6 or more communications, which then became the first book of quantum mechanics. And so he, was pumping out just so much. It's amazing, and it's very strange. But Schrödinger, even though he was a great mathematician and was extremely, good with complex numbers, of course, and comfortable with them, he did not like them. So he wanted a real valued equation. And so we know that he wanted he wanted to interpret the wave function as a kind of continuous distribution of charge traveling through three-dimensional space. We know that then is a problem. But he also wanted a real valued function. And then he discovers one, He calls it the uniform and general wave equation for the scalar field of psi. And then to Planck, he characterizes this as, so it's definitely, he likes it, unheard of simplicity and unheard of beauty. And so what I'll do is first do a little historical detour about this equation. So there he is. He's already got the time-independent equation. Now he wants the time-dependent one. He's having these letters back and forth with Lorentz. Lorentz is 72 years old, and he is, if I learned anything from this, it's like Lorentz is like scary smart. It's almost like, if you read these letters, they're so big and detailed, it's almost like he knows what quantum mechanics is going to be, and he's like sprinkling the crumbs for Schrödinger to go find it. It's amazing. And so he's got all these problems with Schrödinger, what Schrödinger had so far, and he keeps pointing out deficiencies. And in Schrödinger's third communication, he says, what is unpleasant here, and indeed directly to be objected to, is the use of complex numbers. Psi is surely a fundamentally real function, and therefore equation 35 in my third paper, I should be good and write a cosine instead of the exponential, and ask myself, is it possible in addition to define the imaginary part unambiguously without reference to the whole behavior of the quantity in time, but rather referring only to the real quantity itself and its time and space derivatives at the point in time, at the point in question? And so he writes down this equation, and so this was the first time-dependent Schrödinger equation. It's second order in time and fourth order in space. And he calls this evidently the uniform and general equation for the field scalar. In modern form and simplified a bit, it would look like this. And so if we think of, we've got, he already discovered the Klein-Gordon equation, so we've got the real one, the wave. Then he's got Schrödinger complex equation, first order parabolic, and then now we've got this fourth order one in space. But if you just don't look at the right-hand side, it's looking very wave-like. And he loves this equation. He's not put off at all by the fact that the fourth order in space derivative. So he already knew. He just recognized this as, that's just the equation for a vibrating plate, and writes this. And so he was already comfortable with this. And to Planck, he then says, by the way, during the last few days, another heavy stone has been rolled away from my heart. I considerable anxiety over it, but it all resolved itself with unheard of simplicity and unheard of beauty. It all came out exactly as one would have it, quite straightforwardly, quite by itself, and without forcing the true wave function, which is fourth order in the coordinates. By the sixth, though, he abandons it, but he abandons it just for calculation. He says that, what's really real is the real, but I just, for calculation, I'm going to go complex. And so this is, of course, what he's used to, because that's the way it was in classical mechanics, right? You would use a lot of complex numbers, but then you would always, when you compare then to experiment, you would always just pull out the real and then compare that to the observables. And again, he talks about the crudeness, and he really doesn't like the fact that he's going going complex. Eventually he changes, or does he? Well, he starts using the complex only later, but it's not so clear, because he did. So the physicist R.L.W. Chen, who was at Emory, said that Weisskopf told him that Schrödinger persisted in his belief in the real wave function until the end of his days. And then this physicist and historian Ricardo Karam and I both independently wrote to Chen to get this, but Chen unfortunately died, and so we don't know. But I did find that even in 1952 in Nature, Schrödinger is still pointing out that he could get rid of complex numbers in various ways. And so it seems like he still kind of wanted to do that, although I don't think we'll ever really know. Why did he want to get rid of them? We have no idea. Lots of speculation. To me, it just seems natural to use the complex because I can split the complex into real and imaginary in different ways. Chen thought the non-conservative extension was a problem. I think, once he realized, Born's rule, it was then almost like doing it in classical mechanics, because you would ultimately compare the quantity with something real. And so I think that was an issue. I think probability in his theory is going to be an issue. There's many reasons to ditch it. All right, what is this real equation? Well, here's what's going on. So you take so as you know, everyone knows you can take the Schrödinger equation and then put in like polar coordinates, re to the is, and then separate into real and imaginary parts. Then you get two equations, and so you can do that. And so here let's just have u and v be that separating into the real and imaginary parts. But then what you do is you then solve for one in terms of the other, because those two are coupled. Okay, so I forget what slide is next. What's the difference there? Oh yeah, so I solve for one in terms of the other. And so then I can write it all in terms of one. So that's what's going on when he then gets the fourth order thing. So it's not a kind of just, he just squared everything and doubled the solutions. So it's one-to-one solutions between the real equation and the Schrödinger equation that we know and love. So there are various ways you can see that, but you can see that if you're just like counting degrees of freedom, but you could also just map the solutions to solutions. And so you have then this, so what he's trying to do is he's letting the imaginary part be the velocity, writing everything in terms of the real part and its time derivatives. That's the idea. So get rid of the imaginary, write it all in terms of time derivatives of the real. Okay. So there's Chen's with extended to the non-conservative case. And, by the way, this will come up later too, but for those of you who know, Rosen came up with the classical Schrödinger equation in the 50s, and we'll talk about something like that in a little bit. But when you do the classical Schrödinger equation, then the real and imaginary parts, if you're thinking in terms of the amplitude and the phase, they don't couple, and so you can't mimic this in the classical version. But you can do this. So it's I always think of the peculiar feature of the quantum is the fact that the phase and the amplitude are coupled, and so it's in virtue of doing that you're able to solve for one in terms of the other, and then write this fourth order equation.
Craig, just quickly, these are still equations whose solutions are functions of space and time. Yes?
Yeah. So they're not.
What's V?
So one is the u and v are so I've decomposed into real and imaginary parts. So one is what was the imaginary part, and one's the. So I'm taking the imaginary part, and I'm solving. So I get all in terms of. I'm getting it all in. Do I have it all in terms of u or v? So I'm getting it. So I'm writing out v in terms of the time derivative of the other.
Is there a reason why you refer to v as the velocity?
Yes.
Oh, I see. Okay.
Yeah.
I'm sorry. I mean, just because it's a derivative with respect. Okay.
Yeah.
Good.
Oh yeah. Sorry. Yeah. I should have said yes.
But the psi is u plus iv.
Yes. Yeah.
But the redundancy of the overall phase in the wave functions here converts into the redundancy of rotating these variables, right?
Yeah.
So one should.
So I could pick all these different u's and v's. Yeah. So it's not a preferred decomposition into these. There's u prime and v prime and u double. Yeah. There's all of those. Okay. So anyway, he's got this equation. It's second order in time, like the classical wave equation. Takes initial Cauchy data, u and du dt. Unlike the wave equation, it's fourth order in the spatial coordinates. Solutions are one-to-one with the first order complex equation that we know and love. You do have negative energies, it's helpful to have in the back of your mind, the Klein-Gordon equation. The real part is sort of the configuration variable on this picture, and the imaginary part is its velocity. And so you're imagining sort of like, well, maybe it'll be, well, you have multiple representations, so, okay.
By energy, you mean the spectrum of H? The eigenvalues of H?
I mean, you've got, so when I write out the real part, I've got, I've got psi and psi star, and so then I've got the negative energies corresponding to the psi star part. All right, now let's get a little philosophical. I don't know if this is the way to do this, and so we'd love to know if maybe I should think about this differently, but let's just, it might help. So there's all these different ways you can present the Schrödinger equation. They're mathematically equivalent. There's no preferred one, just pragmatic virtues seem to matter, which one to go with. But you could imagine, and I think it is helpful here to remember that Schrödinger back then, at that time, he didn't have the solution of a free particle. So he had a harmonic oscillator, which was nicely contained, going back and forth. And so you could also distinguish that from a kind of position where you might say, well, let's call it real part realism or real realism, where only the real part of the wave function is the beable. And I think from reading Schrödinger there in June that he was a real realist. Now, we'll return to time reversal invariance. And here's the thing I noticed, and I don't really know what to make of, but I think it's something worth noticing, but I don't really know what to make of. How would Schrödinger have understood time reversal invariance if Schrödinger, were time traveled here and he heard of pancakes and not pancakes and all of this stuff? How would he understand all of that? Well, if it was in June where he had the fourth order real wave function, I think he would have said, he would have been working in terms of this, and I say, Schrödinger, just use pancake sense. That's the only one that makes sense. Use pancake, and now we then look at whether this equation is pancake reversible, and it is. So it is because, so this thing, it doesn't flip. So like it's like Green's function, it'll have forms like this, so it's not going to flip over in time. Of course, this will flip, and then it's, it's like a velocity, the velocity of the imaginary part. And so he would then say, well, look, I need to flip this because of this. I'm going to flip my velocity. There's a t.
Sorry, there's something I'm missing. When you use this word pancake thing, the idea is that one should not consider the time derivatives as part of the characterization of the system, or am I missing something?
No, I'm just thinking of what follows from logic and definition alone from t going to minus t. This flips.
But am I supposed to give you? I mean, my problem is that that equation, if you just give me the data of the variable there, is not enough to solve the equation, right?
No, well, it would be just like when you think classical velocity flips. It's just going to be just like that.
I mean, I'm taking a minimal way to make the point is that David's original issue turns on the fact that second order differential equations plausibly can run backwards. Because in the pancake sense, first order differential equations obviously can't, and you frame this into second order form, and so we have that freedom to work.
So I flip this thing, but then if I flip that thing, and I now go back. So what I'm doing is I'm finding out time reversal in a clear place. The real fourth order, second order in time case is, I would say, manifestly time reversal invariant. I then now look at that, and then now I translate back into the complex world, the complex formulation. And when I do that, then of course that's then going to change this which when I then compose to form a complex number is going to be the equivalent to a complex conjugation. And so, well, that's my main point. That I think is really cool, that if I go from the t to minus t in the real formulation, I then switch to complex formulation, boom, I have to do this. Okay? So I think our imagined Schrödinger would say that you need to take the complex conjugate of the wave function when in the complex representation, and it's completely justified in a pancake sense. So problem solved, everybody can sing kumbaya and be happy. Oh yeah, he does have a paper in 31 talking about it and claiming it's time reversal invariant. What the? Oh yeah, so this is, yeah, so again, he's not comfortable either because it's sort of solution-wise, the Schrödinger equation, the complex one, looks hyperbolic, but then it is a parabolic one. Anyway, but my lingering question about this, though, is really this, because does that insight still justify the textbook transformation even if one is not a real realist? So I'm not a real realist. Probably no one is. And so, but on the other hand, that's a real thing, that transformation, and so I don't know exactly what to make of it. It seems like it can't be just a coincidence that when I'm in that real formulation, which is equivalent to the complex formulation, when I do time reversal invariance in the normal, in a good way, and then I translate into the complex, that I have to go side to side star. That can't be a coincidence, and so I don't know exactly what to make of it. So this is me basically trying to pull from you information so I could help, that would help me write a paper for your thing. Okay. Oh, what time did I start?
You are 25 minutes so far.
Okay. Okay, so second way, so remember this is now getting increasingly, maybe you like this, I don't know. I don't think I've ever really mentioned this before to anybody, but maybe this is getting increasingly less defensible. But this is more like motivation than an argument. So Rosen and others, I forget I've got all the references in a couple of different papers, but there's this classical wave function that people came up with. So it was not just Rosen, but a couple of other people independently came up with it. And there's a lot of kind of funny business here in the creation of the classical wave function. And I could talk about this. And so I've been working it out in the last couple of weeks, understanding it better. And then here you have Q, which is, it's very interesting, but Q is the quantum potential that we know from Bohm. And so the classical wave function is basically the Schrödinger form, but with the quantum potential here. And it's a very interesting thing because if I put in R to the EIS into this equation, it kicks out a Hamilton-Jacobi equation and then a continuity equation. And you know when you do it in quantum mechanics, you have a Hamilton-Jacobi equation where you've got the classical potential plus the quantum potential. Here now you have Q is like shifts equations, and so it's sort of like minus the quantum stuff here. And anyway, it's just a kind of it's really more like a kind of soften you up to this picture. Yeah.
What's the classical wave function supposed to represent?
Yeah. So it is. There's two ways of thinking about it. One is in terms of a single particle. Another is thinking of it, the more normal way is thinking about it is really more like classical statistical mechanics. And so I have an ensemble. I can talk about it in the Q&A more than now, but there is all this issue about the single valued versus multi-valued issue here. But yeah, this is going to be the S of the Hamilton-Jacobi equation. And
right. I'm asking a much more flat-footed question. So is it like, is the wave function or the real part of the wave function, say, non-zero only at one point, and it moves around like a particle, or like a classical particle? I take it that's not what's going on?
No.
What's going on? How does it?
Yeah, so so you're getting your trajectory, so it's like a Hamilton-Jacobi where you're getting your trajectories as sort of the normal to the, the wave of S.
Okay.
And then you're going to get a velocity, which is going to be the grad S, which is going to give you the velocity of the particles.
So the solutions to this equation don't, as it were, very directly represent, say, classical particle systems.
So you have so I think we would both agree. So if we went through the creation of this, I think we would both agree that there's some kind of like representational fluff, being added in there to make it look sort of like. So when I was going through the derivation of this, it sort of reminded me of like the second order formulation of Bohm, where you're sort of having a little bit more than is necessary, but it is but it still is. Gives you the same empirical content.
Okay.
Modulo a couple points about the single valuedness.
No, it seems to me that if you play the Bohmian game, but with this equation for the wave equation, then the particles follow Newtonian.
You mean with the Bohmian guidance condition? With
Yeah. So you do V equals grad S, and you're going to get the classical.
So probably in that
things.
sense, you could say it.
But of course then of course it's very different, because if I plug in R to the EIS here and then decompose into real and imaginary parts, then I don't get the coupled between R and S. So the amplitude and the phase don't interact.
But now I
in
don't understand. If I treat it in a Bohm, maybe this is too long. I'm sorry.
And I'm not even sure of what I said.
I
that's right.
certainly can't understand what that might mean, but okay.
Okay. Anyway, well, all of that's now you're sowing the seeds of doubt into people, and it's going to ruin the motivational thing. But here's this classical Schrödinger equation. I ask you, is it time reversal invariant or not time reversal invariant? It's got this, the Q is that's not going to change sign under time reversal invariance in any kind of pancake way. And so if you had been inclined to agree with Callender 2000, you would have looked at this and said, it's not time reversal invariant. This is going to pull out a time, it's first order parabolic equation, and so it's not going to be time reversal invariant. But we know you're wrong, because we built this basically from F equals ma. And we know F equals ma is time reversal invariant. And so all of this elaborate construction has now been built from F equals ma, and so we know that that's time reversal invariant. And so what's kind of interesting in here is that here. Time reversal in this classical thing is implemented by complex conjugation. And so that will take solutions QP to Q minus P, and that's just what's going on in the Schrödinger equation. And so if this doesn't sort of motivate you to, to accept then that the Schrödinger equation is time reversal invariant. So anyway, there's that. Okay, finally, now getting increasingly dodgy. This is then the airplane argument. Shangao has a paper with a derivation of the time reversal invariance in quantum mechanics, and he starts off with the thinking that he's also doing the decomposition into the Hamilton-Jacobi and the continuity equation, and he then says, well, the continuity equation is invariant under time reversal. Why? Because that's reasonable. So that's What I don't want is, invocations of reasonable. I just want logic and definition alone. I don't want what's reasonable. And so, anyway, you could go and look at the derivation. The rest of his thing works out all nicely. But he's thinking, well, what I really need J, the probability current, to turn around. And how in the world can I make J turn around? How? I need the phase and the velocity. I need to think of the velocity as like a phase. How could I do that? And then, oh wait, let's see if this works. Have people seen this derivation of Bohm's theory? Oh, well then you were in for a treat.
30 seconds.
Yeah.
Oh, I hate this. Quotation marks, yeah.
And yeah, so then, where's my, this one? No,
No, it's
this one. PowerPoint?
It's this one. Yeah.
Work on quantum field theory.
Oh, yeah,
Here you go,
thanks.
yeah. And now if you want to go view, you have to go up there to the view. Just one click, full screen mode.
Okay, and so anyway, then the third argument is to do that. And if you then do that, you can then think of that V as a V. The V turns around under time reversal. That's going to turn around the J. The rho isn't going to change. And then you're going to get all the standard operations again for time reversal. And that is it. So conclusion, taking the complex conjugate when time reversing seems utterly convincing when using Schrödinger's fourth order real equation. What does this mean if one is not a real realist? Are we making the same mistake that we do with the classical Schrödinger equation? Yes. Does this tell us that we were paying too much attention to the form of the equations and not enough to the shape of the solution space? Yes. Does the Bohmian hydrodynamic move provide the missing piece, and can other interpretations do similarly? I should say about this, what I really was thinking was, when you go real, when you do the Madelung decomposition of the Schrödinger equation, those equations look just like hydrodynamic equations. The hydrodynamic equations we think of as time reversal invariant, mainly because we think of that flow as the flow of some stuff with some velocity, turn that velocity around, and then the flow goes the other way. And so that was the thinking there behind that. And so 3 different ways of looking at things in a real way, keeping it real, and then that hopefully solves this problem. Thank you.
Thank you. David?
This David?
Yeah.
So let's see, I guess this is just a plea for a more flat-footed story that'll be easier for me to take in. Look, there's been a lot of talk. So you said, look, you look at the real equation, you flip t to minus t, we're done, okay? By contrast, there's been a lot of talk in earlier sessions today about how sensitively what we want to call time reversal symmetry and what we don't depends on ontological decisions that we make, on various kinds of metaphysical decisions that we make. So
Right.
I'd like a more flat-footed story that I can understand about what kind of claims about what there is and what's going on each pancake go together with the kind of picture you've been sketching.
Yeah, good. And then that gets to the sort of question I have about if we're thinking of the first argument, about whether that really works. Yeah, so I think everyone would agree, and as Valia showed nicely this morning, it depends on what you think the ontology is, whether you think things are reversible or not, or have any particular symmetry. And so where things seem clear is, suppose I had an ontology where I thought only the real part of the wave function was sort of the stuff, the beable of the universe.
Right.
And I now write the theory in terms of that beable plus its velocity, what's essentially its velocity.
Right.
And so I think of the imaginary part as the velocity. And that's kind of natural, because you think of the imaginary part as having the time dependence, usually anyway. And so then that theory is then time reversal invariant. And then when I then can translate into the, that same operation of taking reversing the velocity and which we think of as sort of, that's going to be the imaginary part when I collect together and go back into the complex world, then I see that means psi goes to psi star. So that's what I'm clear on, and that's what I think is pretty cool. But then your question is sort of inviting, suppose I'm not a real realist, so I don't think that the real part of the wave function is the beable and the other part is...
And if somebody were to say that, there are obvious worries that arise. Well, the imaginary part is doing some of the shoving around here, okay? Why would we would be tempted to exclude that from the ontology unless we were operating under an ideology that it has to come out time reversal?
Right. Well, this is why I then ended that section with that question, because it seems not, coincidental that this happens. On the other hand, I don't want to be, for those sorts of reasons, I don't want to be a real realist.
Right.
And so I have exactly that sort of unease, because I think, holy shit, this is cool that I go from the real to the complex, and
Famous last word.
Yeah, but then what? How? Yeah. So what I would like really would be a way of saving that insight when I go in, when I rotate back into the complex world, without the ontological baggage of having to be a real realist.
Okay.
That's what I want. I don't know if I can get what I want.
Thanks.
Okay, thank you. I have a technical question about extendability of the real approach. And the worry I have is it's, at least at first glance, it seems to rely on the fact that the Schrödinger Hamiltonian is a real differential operator.
Mm-hmm.
It restricts the operator on the space of real functions. And that's true, of course, but it's not a general feature of wave equations of this kind. So it wouldn't be true if we coupled a particle to a magnetic field. It wouldn't be true for the Dirac equation. Should I worry about that, or does the process generalize to non-real Hamiltonians? I mean, real with respect to a wave function basis.
Yeah, I just don't know. It's apart from, I mean, I could look back in those Chen papers, which are the most advanced things on the fourth order Schrödinger equation that I found. I could look back there and check, but I don't know. I haven't really thought about the Dirac equation just in general in terms of time reversal invariance anyway, but...
Well, like I said, the Schrödinger equation with magnetic potential we did as well. We'd have grad minus IA in the end.
Right. So you're thinking that they're more... So when I do... I have to go back and look at the Chen, really, to be...
I'm thinking in general for the Schrödinger, the non-relativistic ordinary potential Schrödinger equation is very, as you said yourself, it's very close to the fusion equation. It's the only place the complex number appears on the left-hand side of the equation. I'm just concerned that's not a generic feature of the kind of Schrödinger equations we write down, because of how we handle spin, how we handle magnetic fields, relativistic equations. They start getting a bit more thoroughgoing and complex.
Mm-hmm. I mean, I know Schrödinger did have, I mean, Chen is right that Schrödinger had trouble with this, with just even generalizing to the non-conservative case. And so, I mean, Chen then did, but so, I don't know, I have to look.
Not the question I was expecting me to answer to.
Yeah. But to be fair, I couldn't have answered that question even if I wasn't jet lagged. So.
Yeah, I like it a lot, Craig. I think it's going to work, even in quite a lot of generality. And so, especially the first argument, I think it's something that gets rediscovered every 10 years or so in different forms, by Kibble, Gibson, and maybe Ashtekar and Schilling, that you can take quantum mechanics and recast it in a certain classical form, where a lot of the things you were familiar with reappear, and the things that were unfamiliar get sort of dissolved. And this formalism is sometimes called geometric quantum mechanics. But it starts with this sort of thing that so you're really redefining your state space instead of having a complex Hilbert space. That is itself a manifold, so it's very plausible that you could split it into real and complex parts and then say that you now have a 2n-dimensional manifold, which is real, and it's equipped with a complex structure. And if you play with that a little bit, you find a very natural symplectic form and a Riemannian metric. And the symplectic form gives you a classical Hamiltonian theory. It's just classical mechanics. And I guess when I was listening to your talk, I was sort of thinking, one would like out of this a lot more generality than just getting the right behavior of time reversal. You're sort of suggesting we can work in this other framework. And you want to make sure it's really quantum mechanics. And for that, I need things like, I need to know there's the projective symmetry, that up to global phase, everything comes out the same. I need to know how the Born rule looks, and uncertainty relations, and all that. And I think people have kind of worked that out, but and here it just looks to me, why I find it so nice is that this looks to me like the absolute easiest way to see what they're doing, because you've chosen the wave function representation. You're writing down this very simple coupled two differential equation thing instead of the geometric stuff. And so I think, but the small step to connect those two I think would be really, really helpful, because there's some gauge in what you're doing. There's some gauge choices, for example,
right,
when you write down those differential equations that they're not a complete description of the physics.
Mm-hmm.
So basically just full support from me, but I guess I would have thought a little connection to that level of generality would surely be helpful as you move forward with it.
Yeah. This is an answer to that question. I thank you, and yeah, I should look at that as well. But making, two things that just occurred to me that I forgot to say also was, yeah, I could also do that second point with like the Koopman von Neumann stuff. And so there you can think of classical mechanics in a Hilbert space, but now it's not configuration space, but phase space, and you could even have like a Born's rule collapsing. That's then equivalent to classical statistical mechanics, which we still think is time reversal invariant. So the other thing I was going to mention is that, of course, I hadn't talked at all about one other thing when you said about the full generality. Of course, one important thing in quantum mechanics is Born's rule. I'm going to have to write, I'm sure you could do it, but it won't be so pretty.
It is. It's incredibly pretty, really.
It is?
Yeah. Born rule comes out beautifully in this framework.
Oh, yeah, I have to look at that then.
Yeah, I'll show you after. You can see it in a few lines.
And of course, a historical footnote to that is that when Born wrote Born's rule, he didn't do. He just did the square. It was in the footnote, right? Famously, where he just did the square, not the complex. And so the acceptance of the complex at that time was sort of an evolving thing.
But it's sort of, for me, one of the take-homes here is you are showing a sense in which you can view quantum mechanics as an example of the classical theory, viewed as something satisfying the Hamilton equations on the classical phase space, and that's really surprising, right? Usually we say the opposite.
Yeah.
But I think it's lovely.
So this is sort of going back to the comment about representation you made right at the beginning. So this is a slightly facetious question with a serious point to it. So I'm very familiar with the complex number way of representing quantum mechanics, and you now show me the real number way of representing quantum mechanics. But we haven't said anything about the Lego block way of representing quantum mechanics.
About the what?
The Lego block.
Oh, yeah.
I'm interested in more of the details about that goes.
Yeah, it might not be possible. But you could, if I could say to you, David, let this be the Earth and let this be the Moon. Then, with Lego blocks, I would say, let this be, I don't know, hydrogen or something.
It was part be a serious attempt to understand. I've never been completely sure what you had in mind in the level of generality in that paper when it went beyond let's represent a few specific concrete objects and it starts trying to articulate the content of a physical theory.
Right. Yeah. So it might not be possible. So some things might not be rich enough to represent some theories. But it's a mistake to think that what makes one thing about another is. Anything could be about anything. It's just that if some things, I think in the paper we talk about, you wouldn't want to represent, I forget what it was, classical mechanics with a jellyfish because the jellyfish might sting you. And so, so some things are not pragmatically useful.
Any more questions?
Oh boy. That's not good. Sorry.
I just feel sure. I will have to think about it more. It's a nice question when you were saying, I'd like to just see an absolute bare simplicity. Why this expression in classical form, in real form, gives you a ddt that I'll have to put this little t, and then it's equivalent to something where I don't have to do that. How could that possibly be? And that I'm sure it's that coupling that plays the role. And that lives in the symmetry of the inner product in the Hilbert space, the conjugation symmetry. I just feel sure there's got to be a story to tell there. So, I'd love to look at this with you more. It feels tantalizing.
I got sort of help. It really was only just recently that I sort of, I always liked playing around with these kind of. Making classical mechanics look as quantum mechanics as possible and vice versa. And then of course you see the clear differences. And I always worried that the fact that there was the coupling between the phase and the amplitude in the one and not in the other mattered for the time reversal invariance. But here it's sort of the thing is sort of me realizing that I don't think it does. It matters for all of the quantum effects of the world, but it doesn't matter for the time reversal invariance. So that is in the classical Schrödinger equation, the fact that there isn't the coupling doesn't change things. Still time reversal is implemented by the complex conjugation. And in the other case, there is the coupling and I can transform to the real and then just see that as t goes to minus t.
Can thank our speaker again.